All right, class, we're talking about interval problems today. Let's make sure we first know what an interval problem is. Interval problems deal with the motion of an object within that motion a change in acceleration occurs. Now, what you need to do to solve such a problem you need to break up the problem into smaller parts. And what I want to do in this next 15 minutes or so is teach you how to recognize where to break up the problem. Because you're going to break it up into chunks. Now, let's think about throwing a ball. All right, if I just throw you a ball or something, my camera case. All right, if I throw a camera case to you, ready, Mitch? All right, that's 3 intervals of motion. Throw it back. One interval would be in my hand. In order to move the camera case, it's going to accelerate in my hand because I'm pushing on it. Now, since I let go of it, can my hand push on it anymore? So what's the major player? I mean, its motion changes while it's in the air, but because of what? Gravity. It's in a trajectory. Now, when Mitch catches it, or if he throws it back when I catch it, then again, there's another hand putting a force on it, and so it's got a different acceleration than it would if it would have just kept falling when it was in the air. So we'd break such a problem up into 3 parts. You've got, let's say we throw a baseball. You've got the baseball in someone's hand, and they move their hand through some distance. They have thin arms. And then the ball comes out. Now, when that ball comes out, the motion of the ball is dramatically different there than it was before. Now, once it comes out, it's going to fly through the air. That part of this motion would be a trajectory. We haven't taught you about trajectories yet, so you couldn't solve any of that part yet. But you will in about 6 weeks. Now, if that ball runs into somebody's hand, clearly the motion of the ball is different when it's in flight than it is when it's getting caught. So once that ball, maybe it hits a catcher's mitt, it's going to come to rest in his mitt. That motion won't take very long, but that would be the 3rd interval. So if we wanted to analyze the motion of simply throwing a ball and having someone catch it, something that goes on millions of times per day all over this great country of ours, we would need to break that problem up into the throw, the trajectory, and the catch. Because the acceleration of the ball is different while it's being thrown than while it is while it's in the air, than while it is while it's being caught. Thanks. Let's think about another example of a really typical time to break up a problem into an interval problem. If something falls, so let's have a flower pot. If it falls off a ledge, what's it going to do while it's in the air? It'll accelerate due to gravity, right? So this is just a falling object problem. But if it hits the ground, let's say it's muddy today, isn't it going to make a little dent in the ground as it stops? Now, everybody in the room's probably fallen before. When you hit the ground after a fall, does it feel the same as the fall? This is an easy question. The answer to that question is no, hitting the ground hurts a lot. That's why we don't like to fall. It's actually not the fall that we don't like. It's always the landing we don't like. Well, that's because once you land, it's a different interval of motion. You have a much bigger acceleration when you land because all the speed that you gained, if you were falling rather than this flower pot, all the speed you gained in that long fall, all of a sudden you go and stop, right? Now, this moment right there, and this moment right here, and this moment right here, where the acceleration of the object changes, are where you should break the problem up into parts. And there's always one thing that you want to know at that place. And the one thing that you want to know at that place putting a happy face here because that's what you need to know. You want to know the speed right there. Not the average speed along the way or the average speed afterwards. The speed at that one moment in time. It's so useful to know that speed because if you knew how fast it was going right there, if you knew how fast it was going as it left his hand, that's the speed at the end of when the ball left a hand if you're throwing a ball. So what is that for the time it's in your hand? V what? It's VF. But that's the speed at the start of the flight. So it's VI. In interval problems, every time the motion changes, the VF of the first interval is the VI of the next interval. And you won't always have a lot of information about both intervals. You may only have enough information to solve for anything about one of the intervals. But if you can find that speed where the interval changes, then you know the starting speed of the next interval, and then you can keep working your way through the problem. Now, within each interval, all of the equations that you already know apply. All of the thinking that you've already done for all the other kinds of problems applies. So you solve within each interval just like it was all the physics problems you've done so far. It's just now that we've got physics problems that are connected to each other. Let's take a look at the example in the book. It's at the bottom of page 57. In that example problem, let's read it together, make sure we know what it is. A dynamics cart at the top of a ramp accelerates from rest over a distance of 1.8 meters for 1.3 seconds until it reaches the bottom of the ramp. At the bottom of the ramp, it moves on to a level table. Because of friction, the cart begins to slow down at a rate of 2.4 meters per second. How far does the cart move horizontally until it stops? Now you can see we've done the math below there of what you'd have to do to solve the problem. But there's a step in between that I would recommend strongly that you do. Before we go any further, there's a typo in the book. In the box where it says on the ramp, the t is listed as 2.3 seconds in the givens. Can you change that to what it should be, which is 1.3 seconds? That's what it is in the problem, and it's also what it is in the calculation. All right. So here's my recommendation. Organize data in a diagram that shows what's going on in the problem. So in this problem, we had a cart that rolled down a ramp and then it rolled onto a horizontal table. Where are we going to break the interval? I'm going to start tracing with my pen that goes away. As soon as you want to break it up into an interval, you say now. Yeah, right there. Right there, we definitely need to break this problem up. Because what's going to happen to the cart while it's on the table? It's going to accelerate, well, it's accelerating in both places. But the acceleration is different. What will the acceleration on the ramp cause? It's going to gain speed, right? Now, once it's on the table, it will also accelerate, but that acceleration will cause the cart to lose speed. Since the acceleration is different, that means the causes of motion are different, and we need to break the problem up into two parts. Now, once you diagram what's going on, and it doesn't have to be fancy or artsy, although it can be if you're into that, put the data from the problem into the diagram so that you don't mix and match. So what data do we have? We've got a distance, 1.8 meters. Is that on the ramp or on the table? On the ramp. So here's our distance of 1.8 meters. You can see I use brackets like this to show where that distance was from and to. All right, what else do we know on the ramp? We know VI is 0, so that would go here. We know the time. It's that 1.3 seconds, okay? Anything else? Nope, we're done. Do we know anything about on the table? What? Nate? Okay, so we've got an acceleration. It slows down at 2.4 meters per second each second that it's on the table. Now, I'm assuming that you're going to make this way in the problem positive, because that's the direction the cart moves the whole time. If we're going to make that direction positive, what do we need to do to this acceleration? It's got to be negative because its friction's pushing the cart the opposite direction. We also know one more piece of information. It's implied in the problem. What's the cart going to do? Stop. So at some point, VF will be 0 of this interval. Now what we're being asked for is, what's the distance on the table? And you'll see us start to use subscripts like this. And you can see from the book the math we did to do it, we had to find the speed right there. We've got enough information in the problem because we know how far and how long it took for the cart to accelerate down this ramp to find the VF at the end of the ramp. But VF at the end of the ramp is the time where it started on the table. So VF at the end of the ramp is VI on the ramp. Even if, did you notice the problem doesn't ask us to find that? But there's no other way to do it. You have to find that because you don't have enough information on the table to solve for how far it's going to go. But you can get that extra piece of information by analyzing the interval that came first. That speed when the interval transitions is a really critical thing to know in every interval problem. All right?